So once we have finished with the acquisition of the FLIM image, the next step is to measure the instrument response function, so we can implement it in the reconvolution fittings. There are several ways to measure the instrument response function. For those of you who are familiar with the spectroscopy, you may know that this is typically being done with the scattering solution. The problem in microscopy is that most of the detectors used are single photon avalanche diodes because they are very sensitive, but at the same time they are color dependent. This means that their response in the blue, so the excitation wavelength 485, it's different than their response in the green. Here we are using a green filter at 535. Therefore, if we use a scattering light, the response is going to be different, and we cannot use that instrument response function for the measurements. Therefore, we recommend to try to measure the instrument response function exactly with the same settings. This means with the same filter at the detectors. One way to do this is to take a dye which emits in the same region in which you have acquired your FLIM image and quench it further, and quench it with a quenching agent, like for example a salt containing an heavy atom like sodium iodide or potassium iodide. The heavy atom, so the iodide, takes the flow to the triplet state. From there it cannot emit, and therefore the lifetime is quenched. And the dye we like to use for the green is erythrosine B, because it has a starting decay time of 90 picoseconds. If we quench it even further, the lifetime can go to 40 picos, 30 picos, and therefore this is already quite quick and not resolvable by our timing electronics and our setup. Therefore, the measurement of that decay will resemble the quickest decay you can measure. And to prepare the solution of the erythrosine B, the concentration is not really important, so the only thing we need is we just fill a tube like this with water. We take a spatula from the erythrosine B, we just put it here, we dissolve it, and then to quench it further, we add a lot of potassium iodide or a lot of sodium iodide till saturation. We know they are in saturation when we've got here some crystals which are not dissolved. And if you do this, you will notice that you really have to add a lot of salt. So, for the measurement, the idea would be just to record the decay of this dye. And to do this, well, we just put some immersion oil, some immersion medium in our objective. Use a thin cover slip. And we just put a drop. So now the goal is to collect the fluorescence from that drop we have just put here. There are several ways to find what is the best position. You can either do it with the Nikon software. Just you do imaging with internal detectors till you find the brightest spots. Or the quickest, also another quick way to do this is just to go up with the objective till you notice that you lift a little bit the cover slip. Then you go down, just to have the cover slip really plain. And in this position, we should be near the focus should be near the volume. Now we can start a measurement, or a test measurement, better say. And here we can control if we are if we have a scattering or not. So this signal we are obtaining here could be either for the fluorescence of the erythrosine B, or could also be due to the scattering. To make sure it's not really from the scattering light that some part can really go through the filters, because if you excite very hard, we go here to the time trace, and if we are really collecting fluorescence from the solution, what has to happen is that when we move a little bit up in set or a little bit down, the intensity has to remain constant. So to check this, I will just move with my objective up and down. And actually, I see here variations in the intensity. And I see here this very steep spike, and I believe this would be a scattering. So this is the maximum signal, and if I go a little bit down, sorry, a little bit up with the objective, so into the volume, I see that intensity drops a little bit, but not to this level. So I check, I've got here scattering, and I do have, I check that here I've got a decay, and I do have a decay. And now with the time trace, I check if this signal is really constant or not. So I can reset here to 0, and then just move 20 micrometers above and 20 micrometers below, and check that this is constant. If it's constant, it's really, we're really acquiring light from the volume and not from the interface water cover slip, which could be the scattering. So I go here to extra fine. First I move up, and I check that intensity remains constant. It is constant. I go down. And we got that intensity is rather constant. So we know we are in the volume, and we can measure. So to measure, we just acquire this as if it was a FLIM image. So we go to record, and we can stop our measurement with this reaches, well, with this overcoming the maximum 10,000 photons. So now we overcome 10,000 photons, we can stop it. The measurement is safe here, and we can rename it as IRF. Like IRF with 80 through with erythrocene B. Okay, and once we have it here, we can just tell to the software this is an IRF measurement and use it for the analysis.